Good morning, everyone. My name is Maurizio Palesi, and it's a great pleasure to welcome you to the first webinar of the Circle series, which is organized as a part of the dissemination activities of the QUADRATURE project. Today's webinar will be given by Mathias Soeken from Microsoft, who will talk about quantum system architecture for utility scale. The aim of the Circle webinar series is to share knowledge, connect researchers, and open discussions with the broader quantum community. So before introducing our speaker, I'd like to give the floor to Professor Carmen Almudever, coordinator of the QUADRATURE project, who will briefly introduce the project.
Very good morning to everyone. I'm Carmen Almudever, the coordinator of the QUADRATURE project, which is an European EIC Pathfinder project. So the goal of this project is to explore the feasibility of architectures that are composed of multiple chips in order to scale up quantum computing systems, which is one of the main bottlenecks of current quantum computers. To do so, we use a network in package that has a dual character. The first one is a quantum communication link for transferring information between the different QPUs, and the other one is a classical wireless network that is responsible for orchestrating or synchronizing the transfers between the different quantum cores. And both of them operate at cryogenic temperatures. In this project, we also take a full stack perspective, meaning that we go from quantum algorithms and quantum applications down to quantum hardware. To this purpose, we have a consortium that consists of 9 partners, such as UCD Dublin and Equal One in Ireland and University of Siegen in Germany, who work on the quantum hardware itself and in the cavity for transferring information from different QPUs. Then we have TU Delft in the Netherlands and EPFL in Switzerland, working on the transceiver for the classical part of the system. Then UPC at Barcelona and University of Catania in Italy that are developing also the classical communication part together with the required protocols. And last, the Barcelona Supercomputing Center and Universitat Politécnica de Valencia, both in Spain, which are devoted to the higher levels of the stack, meaning the development of compilers for distributed quantum computing and also the applications and the algorithms. So thank you very much for Mathias for giving the first talk of this seminar, and I hope that you enjoy it. Thank you.
Thank you very much, Carmina. I'd like all of you to visit the website of QUADRATURE project, and also please follow our LinkedIn page, where you will find news and announcements for future events. And also please subscribe our YouTube channel, where we upload this webinar and future ones. And now it's time to introduce our speaker, Mathias Soeken, who is a principal quantum architect at the quantum team at Microsoft. From 2015 to 2020, he has been with EPFL as postdoctoral scientist. From 2009 to 2015, he worked at the University of Bremen in Germany and has been a regularly visiting postdoc at UC Berkeley at the group in the group of Robert Brayton. He holds a PhD in computer science from University of Bremen, and his research interests are practical fault-tolerant quantum computing, logic synthesis, and formal verification. So please, Mathias.
Hello. First, I would like to thank Maurizio and Carmen for the opportunity to speak at this webinar, and even the first webinar. So thanks for the invitation, and it's a great pleasure for me to talk to you today about quantum system architecture for utility scale. Like in the project QUADRATURE, for me I'm very passionate about quantum computing at scale. I'm interested about what can we do with quantum computers in the future, especially about the problems for which we think a quantum computer can help in the future. I think fundamentally there are 2 ways to think about quantum computing today and the future. or like algorithms that we can run on quantum computers. One thing is to think about, like, look at the machines that we have today and think about problems and algorithms that we can solve on them. And that's a very interesting task. I look for more towards an other view on it by looking at the problems that we think we can solve with quantum computers, for which we have like found quantum algorithms with advantage over classical ones, and for problems that we cannot solve today, and understanding what machines do we need in order to tackle these interesting problems. And that's what we call utility scale. So let me go a bit more precise about this definition of like quantum computing at utility scale. So it's about solving a problem that we can't do classically. Our initial definition was a bit more stringent to say, yes, a quantum machine that can solve an interesting but classically intractable problem. Actually, not just to show that we can solve something that we cannot do classically, but it also should be interesting. It should be of interest to us as a problem that solves something for which a solution is something that makes our lives better, for example. We have further strengthened this definition in the past, not looking at only to solve it, but we also want to understand the impact of the problem and the cost of solving this problem with a quantum computer. So the more stringent definition is that can we solve a problem whose value of knowing the solution to it exceeds the cost of the quantum computation. That means if the value is not so high, then maybe it's not worth building a quantum computer. We could look for other avenues to solve this problem. But on the contrary, it also means if the value is very high of solving this problem, it also means that it's okay for the quantum computer to be advanced, to be complex, to require many resources in order to solve this problem whose value exceeds the cost of running this quantum computation. So we often look at this kind of scale when we think about quantum computing. Why? Because the fundamental advantage that drives us to even look at quantum computing is that we can solve quantum algorithms at a conceptually better asymptotic complexity than classical counterparts. But we can find that some problems with classical computers have some specific lower bound on the complexity that we need to solve this problem. That means how do the number of steps grow in order to solve a specific problem in terms of the input size. And no matter what we do, no matter how we build these classical computers, since they all are based on the classical Turing machine, we cannot break these kind of complexity barriers because they are not dependent on the type of way we build a classical computer, but the type of the information that is underlying. In quantum computing, we don't rely on this Turing machine model. We have a different model, and therefore we can overcome this barrier and maybe solve some problems in a lower complexity. So it means the number of steps we need to execute in order to solve a problem with respect to the number of input size is less. But this makes them conceptually faster because we have to perform fewer steps. But the time to execute one of these steps on a quantum computer can be significantly higher, much, much, much higher. Multiple magnitudes, out of magnitudes higher, and we're going to see some examples of it. That means that the cutoff point in which we're actually faster than a classical computer depends on the crossing point. That is, when is the number of steps multiplied by the time it takes to do one step better than the number of steps in the classical computer times the time it takes it to execute it there. And this crossover point is important to consider to decide if we have practical quantum advantage at a utility scale. First, what is the problem size at this crossover point? Is it a realistic problem size? For example, let's take cryptography as one example for quantum computers. If the crossover point as a problem size of millions of bits in key size, and it's not interesting because we don't do cryptography with millions of bits of key size. We do a couple of thousand bits of key size. It could be interesting anyway because we want to prove that we cannot do cryptography, but this would be an example of where we wouldn't have quantum advantage if it were like this. Another important factor is the time it takes to solve this problem. If it takes 10 billion years to solve a problem classically, and it takes 10 million years to solve a problem quantumly, it's much faster, but it's still intractable because we don't want to wait that much. So the time we want to hit this crossover point should be within a couple of weeks, maybe. Depends, of course, on the problem, like how we can solve it, but like a reasonable amount of time is like, yeah, maybe less than a week, maybe less than a month. And the problem side should be something that is interesting for us to solve. So why is this? Why is there even this crossover point? As I mentioned before, is that quantum computers are really, really slow. And here's just an example of like some characteristics of a NVIDIA GPU chip and the hypothetical quantum computing chip from the for future quantum development. So the logical time step in a GPU like this would be like 0.7 nanoseconds time step. Whereas in like in a quantum computer, this could be like 10 microseconds, maybe 1 microsecond of logical time step to do one logical operation. That is much, much, much lower. That means that the time to do 116-bit floating point operations, something like we can do 2.1 petaflops in a second with a GPU, and we can do 10 kiloflops in this, per second with a quantum chip. And also the bandwidth is like very different. We can load a lot of data in a classic computer, maybe like 38,000 gigabit per second, whereas maybe something like 1 gigabit per second in a quantum computer. So we have these really big differences between the operation speed of a quantum computer compared to a classic computer. That's why the complexity advantage only kicks in after some time. But what complexity advantage do we need for this? Is it enough to have like a quadratic speed up, like we do in Grover's operation, in Grover's algorithm? We don't think that this is the case. So let's consider we have to do in this Grover style optimization algorithm, we do something like n oracle calls. So n times we have to execute some expensive functions. And let's say this could be like a floating point operation that is part of this oracle call. Then the quantum computer can do less than these calls. It can do square root of n of these calls. But if n were if this oracle would be just consisting of like one floating point operation, given the characteristics of the machine that I showed before, then the crossover point would be at like 1 year, where really the quantum computer would make an advantage compared to the classic computer. And if we had like 1,000 floating point operations, which is like maybe more realistic to something that happens inside these oracles, the crossover time would be after 1 millennium. And for concrete problems like protein folding, if you want to do apply Grover search algorithm for optimization in this kind of like application, the crossover time would be at the age of the universe. So because of this large gap in operating times, we think like it's not enough to have super quadratic speed up. So what's enough? What do we need, or what is sufficient? If we had quadratic speed up, right, like how many operations can we do in a practical crossover time, like less than a month? So 0.001 with quadratic speed up. With cubic speed up, we could already do like 3,000. So there we get into a regime where this is interesting. So we could do like 3,000 floating point operations within a month or within a reasonable time. So then we could probably find some algorithm of applications that requires as many resources and get some speed up. If we had quartic speed up, we want to have like, we can perform like 400,000. So the exponent matters here, and going from like quadratic to cubic speed up or quartic speed up makes a big difference. And there are some problems in the domain of cubic speed up and quartic speed up. But ideally, we have like exponential speed up. And with super polynomial quantum speed up, we have a lot of different kind of problems where we can excel quantum computing. And here in this maze, I want to show I'm showing some examples of where we can show super polynomial speed up for quantum algorithms. And here quantum computers could really, really shine. So like, for example, better batteries, improved drug efficacy, new materials, clean water cryptanalysis, that is where we can get exponential speed up and solve these problems, instances that we cannot solve classically. Whereas the other ones that are folded out are based on algorithm speed ups that are not super polynomial, in which we don't expect this kind of don't expect a practical advantage of quantum computers due to the large gap in operating times for single operations. All these problems that are highlighted here, except for cryptanalysis, are based on quantum chemistry simulation. And they work so well because nature computers quantum, and if we apply quantum computers based on the same principles, we can solve these problems in nature better. So how do we want to build this? And we don't in Microsoft we envision a compute platform in which quantum computing is a part of a larger ecosystem, composed not only of quantum computing, but also composed of AI and high performance computing, HPC. And all these three would work together to solve a problem. In the end, what's important also to know is we're interested in solving problems that we have no answer for today. Any way of solving this problem is interesting to us. If we don't need a quantum computer, the better, because probably we can solve it maybe today. So it's interesting to us to find exactly these parts in the process of solving a problem where we require a quantum computer. And that may be a subpart of an overall computing chain in which we use different things alongside quantum computing, also AI and high performance computing. One more example of what we kind of aim to solve with AI and quantum computing is something like self-healing materials, coolants without forever chemicals, or better batteries. And I said, we maybe don't need quantum computing, so sometimes we get away without quantum computing. And here's one example of something we have done, I think it was last year, where we applied a high-performance and AI computing stack to find a better battery. And this is essentially a discovery of a large search space of possible material candidates. So you want to find a specific material that solves some specific problem, and you have to find the needle in the haystack. You start off with a lot of different candidates that could potentially be the solution you're looking for. In this case, it was more than 32 million materials. And if you would explore them one by one, you would probably spend something like 20 years. So you need some better filtering, some better techniques to bring this down. And we brought this down to about 80 hours. And it starts by using AI inference techniques to bring this down from 32 million to something like 600,000, 200,000, 8,000, up to 771, based on different kind of techniques that allow to filter out some of these candidates which are not viable. Then we left with these 771, which are okay, there is something interesting in there, but we are at our limits with the techniques we have used so far. So we have to go deeper and find some stronger techniques, and that's where we use HPC screening. So we apply some complicated quantum chemistry algorithms like density field theory and molecular dynamics on high performance computing to further filter down these 771 candidates to 74. And then we're starting, so then we at a point where we can still further not find with automatic tools, high performance computing, AI, and crack this list further down. And now we're getting into a mode where we also need expert guided AI models. So we have human informed validation, but instead of starting with 32 million, we're now at 74. So this can be done in faster time until this breaks down to one candidate, which was a new electrolyte that was found to build a better battery. And then we have built the battery and it powered something. And that was something you can do today with current techniques without using a quantum computer. But we have also found cases in which we can't do this. So for example, this is a reaction network for catalysis workflow. So in this paper, we also try quantum chemistry techniques to understand these, to fully simulate this reaction network, to understand the intrinsics that's going on in this problem. And we start with compute-heavy quantum chemistry algorithms on classic computers using HPC with DFT exploration, starting with more than 1 million configurations. Then we're left with some that are not applicable to this technique because it may not be strong enough. So we do further energy refinement using more than 3,000 CCSD-T calculations, which are more compute heavy than DFT. And then multi-reference diagnosis on more than 20 configurations. And even that breaks down for some of them, but that leaves us 5 for which we found, okay, classic compute was not able to give us any information about these 5 reaction networks, 5 configurations to consider. So these are now exactly the 5 candidates that are interesting to solve on the quantum computer. So we would need a quantum computer to do that, to fully understand this catalysis workflow, to get a whole picture of and solving this complete problem that we're interested in this case. Let's take a look more on this, because this is one of our main applications we look at is quantum chemistry. So let's look at the landscape of quantum chemistry algorithms. So you see on the y-axis the cost of applying this algorithm, on the x-axis the simulation accuracy. And what we can expect is the higher accuracy you want to need, the higher is the cost of computing. But not only the higher the cost of computing, it also changes the complexity class in which we are in, from something polynomial to superpolynomial exponential. So in protein folding would be the technique with the lowest simulation accuracy on this plot, which can be done with classical mechanics. Drug discovery is semi-empirical. Then this is what we've seen before, density functional theory for understanding the electronic structure. To understand chemical bonds and reactions, we can use this coupled cluster CCSD or CCSD-T. And then to understand the full entanglement, we need what's called the complete active space configuration interaction. And that is an algorithm that is we regard exponential time, so it's not applicable to large instances. And here we have alternatives, quantum algorithms that have superpolynomial and exponential, lower complexity. So that is the line in which the quantum computer could make a difference. So everything below, classical techniques, but everything above coupled cluster, quantum computer can do this difference. So it's really important to understand also which of these problems we want to which of the parts in this big reaction network require what kind of simulation accuracy, or what do we want to use the quantum computer for, do we not. But even these other ones, they're don't require a quantum computer, but doesn't mean they're simple to use. They're not they still use a lot of compute. They still need a lot of hours in high-performance computers on supercomputers that run in the cloud. So what people have done is they took the results of these simulations and fed them into an AI model, so that we can, instead of redoing, or instead of applying these heavy computing, compute-heavy computations on new instances, to instead use a less compute-heavy AI model to interfere the solution based on a new model they found. So we train an AI model on results that we have seen, and then instead of redoing the computation as compute-heavy, instead of using the AI model, and this will also bring down the complexity. This requires, of course, to have this data to train the AI model, and you have to get this data from applying these heavy computations. So you, instead of just and it's kind of ecological, because instead of just applying the computation to solve the specific problem at hand, you save the result and reuse it also to train an AI model alongside with other results to make it faster for other problems that come without applying the difficult technique. And we can do the same thing with quantum once we have run the quantum computer and once we have gotten some results from that. So we get more high accuracy results from the quantum computer. We also feed this into the AI, and we can hope that we have to do even less applications of the quantum computer to new problems, but can reuse what we have learned in our AI model. So to look at this in a different view, and let's say you have this target molecule, you perform an HPC simulation, you do AI training, you get a classical AI model, and then when you do the AI interference, it's faster. But if you have quantum, you use the AI training also to have a more refined quantum model with this information from there, and you get also now similarly as fast interference as before, because it's the same process, but more accurate results because it has been trained with more accurate data from the start. So we have talked a lot about chemistry. I just want to show dive in one more time in this chemistry algorithms, and we see like a lot of improvements on the algorithm side. It's often, yeah, I want to say like we don't pay too much focus on algorithm improvement often when we talk about computers. We know like from classical computers that Moore's law has guided like very, very fast computers in the past, with like doubling the compute speed every 18 months until it hit a scale, until it hit a limit. But we have seen some similar scaling, if not faster scaling, on classical algorithm side. When we look at like algorithms and the improvement that algorithms made in like bringing down the complexity, often we see some faster results there. So while we're building better quantum computers with more accuracy, faster and smaller ones, we also perform, of course, optimizations on the quantum algorithms. And this is after you have shown that you have a better complexity. That's the first step, showing you can solve a problem in a lower complexity classically, ideally superpolynomial. But then it's still a question like, how do you implement this? What is the cost of one step? So after showing this, you have to implement the quantum algorithm, and there's also different variations to do this, and we have seen a lot of breakthrough in this in the past. For example, here, this is the quantum simulation algorithm that is underlying all these problems that I've shown in the previous slides, starting with estimations of that require like millions of years of runtime to tackle these quantum chemistry problems in 2014. And then you get like improvements every couple of years, like with a 10 million-fold acceleration to about 1 month of runtime, then another 1,000-fold acceleration, then another factor of 20, another factor of 6, and that's where we are today, which allows you to solve these problems faster, and faster. So you're getting to the problem from two parts, right? You're building better quantum computers, but also you lower the requirements to solve the quantum algorithm by finding better quantum implementations. And when these two meet, then you have practical quantum computing at scale, because now you are ready to have to solve the problem with a given hardware. But it's not only that. It also allows you to relax your requirements on the quantum computer. If you make really good improvements in quantum algorithm implementations, and you get to something, I can solve this problem. I can solve this problem. I would need something like 5,000 logical qubits, but I only need 10 seconds. Right? You may be at this part. Then it's still a challenge to handle 5,000 logical qubits, but 10 seconds doesn't seem to be a problem. So what you can do, you can relax also some constraints on your quantum computer. You say, instead of solving this in 10 seconds, let me solve it in 10 minutes, and I can relax the requirements on the logical cycle time on the computer. So it also helps us to understand, okay, where do we need to get to? Is scaling up the qubits a problem? Is scaling up the speed of the qubits a problem? Is scaling up the quality of the qubits a problem? We want to do all of this, but like we have some kind of room in like where we want to put focus on. And this, especially this acceleration to runtime in these quantum algorithms, help us to relax the necessary logical cycle time. In here, it was something like we need like 10 nanoseconds of logical cycle time. That's like really fast, what you would expect from the quantum computer. Whereas now for these applications, we'd say maybe we can get away with like 100 microseconds logical cycle time to solve these applications still in reasonable amount of time. So the quantum computers are computational accelerators together with GPUs, or like similar to like GPUs or FPGAs. And we think of them living in a cloud. In Microsoft, it would be Azure. So you have hyperscale workloads, you have developer tools to implement these workloads, to orchestrate these workloads into different compute parts. Then you have cloud services that access the compute hardware. And this may be like general computers, it may be FPGAs, maybe GPUs, it may be AI accelerators, and it may be like quantum computers. Those quantum computers from Microsoft or third-party quantum hardware. And you would develop your workloads with something like developer tools or Copilot. You have libraries, AI models. But this is like how you, as a developer, you look at solving this kind of problem, and you just want to have access to like a lot of different computers. Make sure that you send the problems to the right computer to solve your task. We're going to focus today on the quantum part of it. So the quantum accelerator is broken down further like this. We have a quantum driver. We have developer tools in which we develop our quantum programs, or we express the algorithms in terms of quantum programs that we want to solve, and we can optimize them even hardware agnostically already, same way we do like classical programming. We want to, of course, have some developer tools with a friendly interface to the computer. The same way we don't write assembler today anymore, we also expect that we can program a quantum computer in something higher, in a high abstraction than assembler, possibly reusing the same language among different architectures and computers, breaking this down further in the stack of the compiler. We'll be here in the quantum driver, we optimize the code then for a specific quantum system to the specific intrinsics that the quantum system provides. We execute the classical part of the application. And this is still on like the classical part around the quantum computation. And we allocate qubits and anything else that we need to execute this quantum program. With the quantum engine, we have like the more control with the hardware, the interface between the hardware and the software, where we bring up and tune qubits. We transform logical operations into physical ones that are error-corrected. We send control pulses to the qubits. We perform and process measurements, bring them back to the application level, and perform also quantum error correction. And then down the quantum plane is like where the QPU, where the chip lives, the quantum core. So we have this is another view on it. We have the stack, the quantum computer stack, going from a high-level algorithm. We have a hardware-agnostic quantum unit representation. This goes into the quantum driver, making it a hardware non-agnostic executable. We express in terms of logical qubit instructions. These have to be like implemented physically by taking into account error correction, because qubits are very noisy. And then we apply these physical operations, and we control the hardware, where we like send pulses to the qubits to perform an operation, but then get also information back when we do something like measurement, and we get a measurement result that we have to then take into account either an error correction or an application level. And this is just like, maybe to go back to the slide, because, this is just for one core. I'm not even talking about yet quantum networking that is like part of the project, which makes this problem not simpler. So this is just going on in one core. So what is kind of like the information that goes back and forth here? And as I will soon show, in a system like the one that we built, like the Mariana-based quantum computer, all the operations that we execute are measurement operations. So there are no gates in a Mariana-based computer. These are all measurements. That means it's not only that we issue operations, we also receive back measurement results from these operations. So a typical application instance for a complicated quantum chemistry problem that we cannot solve classically would require something like, if we do the resource estimation, if we try to like match the budget of like running this in a reasonable time, less than a month, that would be like something like less than 10 million instructions per second. These are like high-level logical operations. Like high-level operation in our quantum program, which maybe like when we break them down into logic operations, about like 100 million. So on the quantum ISA, is maybe something like a C0, right, is one of the instructions, and the logic ops is maybe like the measurement sequence that is used to implement a C0 on this device. Also on the high level of the application, we have very few measurements, right? We have maybe some measurements at the end of the computation to get the result back, or we have maybe some mid-circuit measurements to do tricks like measurement-based uncomputation of components and something like this. But normally we don't find many measurements in the logical representation of our program. If we do our logical ops, then we have more measurements because now we broke down our quantum ISA, like our CNORs, Hadamard gates, into measurements that are part of the Majorana architecture. But these are not error corrected. So now these operations have to be error corrected with to map them to physical operations on the quantum computer and physical qubits. And that has another overhead of like maybe bringing it to like 10 to the power of 12 instructions per second. That means 10 to the power of 12 measurements per second. 10 terabit of second per communication. That has to come from the hardware back to the quantum engine. So that is a lot of data. And that is like something that we see we need to have if we want to solve an application in this time. So all this the analysis of looking at this application to find the best algorithms gives us some footprint like this. Which then helps us to understand, okay, what does our hardware need to support in order to achieve this? How can we make this happen? Probably the first two layers are something, yeah, we could probably get to do this, but the bottleneck is in the lower level, at the physical operation level. How can we do this control and the readout at scale? The idea is what we have for this is doing the following. We're using a cryo-CMOS control in the code to issue these 10 to the power of 12 instructions without heating. And the key is that we can do this digitally. Now I'll show this when I show like how our hardware works and why we can do this digitally. And then for the readout, we're going to use a room temperature ADC and measurement processing to do this to cope with the power demands for readout at room temperature. So it's shown here. The the physical instructions are issued in the code, but then with analog signals, we get out the data, measurement data, and then the readout and the symbol decoding for error correction is done at room temperature. And this we think we can do. So that helps us to also to then plan the architecture, right? Going from like, where are the bottlenecks, where's the information flow, how can we where should we do specific parts? Because we didn't see a way of like, okay, how can we do these measurements in the cold without heating up the system? So why is it like the case? Just a small look into error correction. What you see here is one logical qubit. It corresponds to one logical qubit in your application, encoded using a surface code of distance 7. So this is 7. So you like the white dots that you see in the grid are like the data qubits. The black dots are helper qubits, and you have like a 7 by 7 square of data qubits. This is like a distance 7 surface code that gives you some protection against logical errors. The size we require for practical quantum computing ranges maybe from with 10 to the minus 5 error rates of something like 9 to maybe even 20 or above 20 distance. So it will be like, instead of this 7 by 7, you would see in the worst case maybe like a 21 by 21 grid of qubits. Right? These are all qubits. All the dots, the white dots and the black dots, are physical qubits now to represent one logical qubit. And then the lines you see with the letters like Z, X, ZZ, and XX are physical quantum operations on the machine. In this case, there's no gates. These are all measurements. These are either single qubit measurements, or there are non-destructive joint measurements between two qubits. Either XX or ZZ. And that's how we can implement the operation. And this is like we see now, it's at time 1, this is at one time step, all these operations take place on all the logical qubits in your computer. This happens all at the same time. That's why we get to 10 to the minus 12 measurements or instructions per second. And then it's like step 2, steps 3, and step 4. These are like, it's a scheduling of these operations. These 4 steps make up one syndrome extraction measurement to get information about the state of the qubits to possibly correct them. In order to achieve the required logical error rate, you have to repeat this process now, in this case, 7 times the number of distance. In the case of 21 times these 4 steps. This is one logical cycle. And so this is what we want to squeeze into something like 1 microsecond, 10 microsecond. This has to happen all at this time. So we to do this, it's like the digital voltage control is key to this, and we think we can control our topological qubits in this way. I want to show like a little bit about this. I'm a quantum software architect, so my focus is on software, but I want to give you like a brief overview on also the hardware. But I invite you also to learn more about this on our webpage, forum.microsoft.com. This is our Mariano 1 chip that we have shown earlier this year. The next slide. Here. So what we're doing now is just a really rough overview on Mariana qubits that we built. We take a superconductor. It looks like this in room temperature. And then we can cool it down to a couple of millikelvin, and then you get this Cooper pairs electrons. Then you replace this superconductor on top of a semiconductor nanowire. And we make this like really fine, right? Semiconductor is really small, and the superconductor on top of this, and the fabrication process is very difficult. So we put them together, we get a superconductor. And then, so this is like you see in this picture on the left-hand side, right? This is really built atom by atom. The semiconductor on the bottom, the superconductor on the top. And then you apply magnetic field. When you apply this magnetic field, you get something, a topological gap. And in that topological gap, you can create this new phase of matter, which is called topological phase. And this topological phase, so you apply this magnetic field and voltage, you get the topological phase. Then you get 2 Majorana zero modes at the end of this nanowire. And if you take them and you bring them together, they either combine and you get a 1, or you bring them together and they collapse and you get a 0. This is how these, in a very abstract level, work. So you do very fast and accurate measurements of these to distinguish 0 and 1, and a very precise building of these nanowires. And we do this with the measurement is done with a quantum dot, and you essentially measure like the parity to distinguish the parity of electrons to distinguish between even states and odd states. And you can do this with a if you do it very precisely, you can get a very reliable error rate. So they're like, because they have some inherently topological protection, we can get very high error rates. We can also make them very, very small because they're like semiconductors, superconductors. And they can be very, very fast because we can control them digitally. And these are like 3 ingredients that we need to meet scalable quantum computing scale, practical quantum computing scale, fast qubits, small qubits, and highly reliable qubits. Because the more reliable the qubits are physically, the less burden on error correction. So if you take one of these wires, you can essentially still have a classical bit. You need 2 of these wires to distinguish also between Z and X direction. So this would, and then you connect them with gates. These are the pink ones, and the quantum dots, which are the purple ones. And you can build these loops by controlling the quantum dots. And then you can make this loop, for example, to do Z measurement. You can do this loop that goes to the top wire and the bottom wire. Now we have 2 qubits, the one on the left, one on the right. You make a Y measurement. You can loop between 2 qubits. You get this XX measurement. And you can do a loop again at the bottom to make a Z measurement. Similarly, you can get a ZZ measurements by doing a loop with 2 qubits that are vertically stacked. And like this, you can build this computation. And these are like the main primitives you have, like single qubit measurement and 2 qubit measurement. And you can, together with like single qubit preparation into one of these Pauli states, you can build all quantum computers, all quantum computation, plus non-Clifford operations. Right. So to conclude, really driven by what application we solve, to understand what kind of parts are important in the process of solving this problem. Is it like AI? Is it HPC? Is it quantum? Is it all three of them? And the most difficult problems will have all three of them. Designing, finding first the problems that we need to solve, understanding the requirements to the hardware that we do that, and then building a stack that can bring down the problem into something physical, understanding the limitations between the different abstraction levels, and finding the right hardware that solves the problem for us. Thank you.